Hey guys, tonight we begin with something so ordinary that most people never think about it. Water. It falls from the sky, fills rivers, disappears into the ground, and stubbornly refuses to travel uphill no matter how politely you ask. Ancient people understood this very well because, unlike us, they couldn't simply twist a tap and expect water to appear from nowhere. Every drop mattered. Every bucket required effort. Every city depended on solving one simple but frustrating problem. How do you bring huge amounts of water to thousands of people when the source is miles away? The Romans looked at that problem and responded in the most Roman way possible. They decided the solution would not be small, practical, or easy. It would be enormous, precise, and just complicated enough to make future civilizations wonder if they secretly possessed magic. Long before aqueducts stretched across valleys and before fountains decorated public squares, Roman settlements faced the same difficulties as every other growing community. People needed water close by. Rivers helped, springs helped, wells helped, but populations expanded faster than convenient water sources. As towns became cities and cities became centers of trade, government, and military power, local supplies stopped being enough. Suddenly, water wasn't just something you drank. It was needed for baths, fountains, workshops, laundries, gardens, public buildings, and countless daily activities. A city could survive without luxury, but it could not survive without water. Somewhere in the Roman world, an engineer likely stood staring at a distant mountain spring while imagining a future where that water somehow arrived inside the city. Most people would have called the idea impossible. Roman engineers called it a project. The first challenge seemed simple. Water had to travel great distances without pumps, engines, electricity, or any of the conveniences modern people take for granted. There would be no giant machines forcing water forward, no hidden motors humming quietly underground. Only gravity. The same force that drops apples from trees and causes people to regret climbing steep hills. Fortunately, gravity is reliable. Unlike politicians, weather, and construction schedules, gravity almost never changes its mind. The Romans understood that if water started from a point higher than its destination, gravity would do all the work for free. Free labor is historically difficult to resist, so they searched for springs and water sources located above the cities they wanted to supply. Once they found one, the real challenge began. The water couldn't simply rush downhill in a straight line. Nature rarely provides convenient routes. Between source and destination stood hills, valleys, forests, rocky terrain, rivers, and countless opportunities for everything to go horribly wrong. The solution required extraordinary patience. Roman surveyors walked landscapes carefully, measuring slopes with remarkable precision. They weren't searching for the shortest route. They were searching for the smartest route. A path where water could flow continuously downhill without moving too fast or too slow. Too steep, and the current would become destructive. Too shallow, and it would stop entirely. Somewhere between disaster and disappointment existed the perfect gradient. Finding it became an obsession. Teams spent months surveying terrain, marking routes, adjusting calculations, and arguing over measurements that looked insignificant but mattered enormously. A difference of only a few centimeters across long distances could determine whether an entire aqueduct succeeded or failed. Imagine spending years building a massive water system only to discover the water refuses to move because someone miscalculated by the width of a finger. Roman engineers found this possibility deeply upsetting and therefore measured everything repeatedly. Once a route was established, construction began. Contrary to popular imagination, most aqueducts were not giant bridges. The famous arches visible today represented only a small portion of the overall system. Most aqueduct channels actually ran underground, where they were protected from weather, enemies, and curious individuals who might decide a public water supply looked useful for personal projects. Underground channels also helped maintain stable temperatures and reduced evaporation. The water traveled through carefully lined conduits, descending gradually mile after mile. Workers carved tunnels through hills, cut channels into rock, and built retaining walls wherever necessary. The scale of the effort was staggering. Entire teams labored for years so water could perform an activity it was already inclined to do naturally. Yet that was the genius of Roman engineering. They never tried forcing nature to cooperate. They simply convinced nature to help. As the water moved closer to cities, the system became increasingly sophisticated. Sedimentation tanks allowed dirt and debris to settle before entering urban networks. Inspection shafts permitted maintenance crews to access underground sections. Diversion channels controlled flow rates. Everything served a purpose. Nothing existed by accident. The result was a network so reliable that many Roman cities enjoyed cleaner and more abundant water supplies than communities that would exist more than 1,000 years later. Citizens likely took this miracle for granted because humans adapt to convenience with astonishing speed. One day, you're celebrating an engineering triumph. A few months later, people are complaining the fountain near their house isn't decorative enough. Water eventually reached distribution points where it could be directed throughout the city. Public fountains provided access for ordinary citizens. Bath complexes consumed enormous quantities. Wealthier households sometimes secured private connections. Industrial operations depended upon steady flow. Everywhere the water traveled, it transformed daily life. Streets became cleaner. Public health improved. Economic activity expanded. Entire neighborhoods developed around reliable access to fresh water. Yet perhaps the most remarkable aspect remained invisible. The water never stopped following gravity. Not once. Not for a moment. Every apparent miracle concealed simple physical laws operating with extraordinary consistency. Roman engineers did not defeat nature. They mastered understanding it. And in doing so, they created systems so impressive that centuries later, people would still stand beneath ancient aqueducts asking the same question. How did they do this without modern technology? The answer is both simple and astonishing. They paid attention. They observed how water behaved. They respected its limitations. They designed around reality instead of arguing with it. And somehow that approach proved powerful enough to supply entire cities. As the Roman world expanded, aqueducts multiplied. New settlements demanded water. Existing cities demanded more. Each project introduced fresh challenges. Some crossed difficult terrain. Others required tunnels extending through mountains. Every landscape presented unique obstacles. Every obstacle required creative solutions. Yet the underlying principle remained unchanged. Start high, move gradually downward. Let gravity handle the rest. It sounds obvious now because success often disguises complexity. But imagine conceiving such systems without modern surveying equipment, advanced mathematics software, satellite imagery, or industrial machinery. Everything depended upon skill, experience, observation, and relentless attention to detail. Mistakes carried enormous consequences. Success produced thriving cities. Failure produced very expensive ditches. Roman engineers preferred the first outcome. Over time, these water systems became symbols of Roman power. Conquered territories received roads, laws, architecture, and increasingly aqueducts. Clean water represented civilization itself. Where aqueducts appeared, urban life flourished. Fountains sparkled in public squares. Baths welcomed crowds. Markets expanded. Agriculture improved. The empire literally flowed on water, carried from distant sources by channels stretching across entire landscapes. Visitors arriving from regions without comparable infrastructure must have viewed these systems with genuine amazement. Water appeared where it was needed. Cities thrived in places that otherwise could not support large populations. Everyday convenience masked extraordinary engineering. And perhaps that was the greatest achievement of all. When engineering works perfectly, people stop noticing it. They simply assume life has always functioned that way. Yet beneath every Roman fountain stood countless calculations, measurements, laborers, surveyors, stonecutters, planners, and engineers. Their work transformed gravity from an ordinary force into the foundation of one of history's most impressive infrastructure networks. Water flowed, cities grew, empires expanded, and all because a civilization decided that rather than complain about gravity, it might as well put gravity to work. As impressive as the aqueducts were, eventually the Romans encountered a problem that even confidence, determination, and an unhealthy enthusiasm for construction could not easily solve. Landscapes are rarely cooperative. A water channel moving steadily downhill works beautifully until it meets something inconvenient. A deep valley, a steep gorge, a wide depression in the land that seems specifically designed to mock engineers. Standing on the edge of such a valley, a Roman surveyor faced two unpleasant options. The first was to build a massive bridge carrying the channel across the gap. This approach certainly looked impressive and gave future tourists something to photograph, but it also required enormous quantities of stone, labor, and time. The second option was finding a smarter solution. Roman engineers generally enjoyed looking smarter than the landscape. This is where the story becomes interesting because it introduces one of the most misunderstood achievements in Roman water engineering: the inverted siphon. The name sounds mysterious enough to belong in a magician's handbook, but the principle behind it is surprisingly straightforward. Imagine water arriving at the edge of a valley. Instead of continuing across a bridge, the Romans could guide it into a sealed pipe. The pipe descended sharply into the valley floor before climbing the opposite side. To anyone watching, it appeared the water would become trapped. After all, water runs downhill. Everyone knows that. Yet somehow it emerged on the far side and continued its journey. To ancient observers, this must have seemed suspiciously close to sorcery. It was not sorcery. It was pressure. Water descending into the valley gained energy. The deeper it traveled, the greater the pressure building within the sealed pipe. By the time it reached the bottom, gravity had effectively loaded a giant spring. The accumulated pressure then pushed the water upward along the opposite side. Not above its original starting point, because gravity still refused to compromise its principles, but high enough to continue moving toward the city. The water had not violated any laws of nature. It had simply obeyed them more cleverly than expected. Roman engineers exploited this behavior with remarkable skill. They calculated depths, pipe strengths, flow rates, and pressure requirements with impressive accuracy. Mistakes could be catastrophic. Water under pressure is not forgiving. If a joint failed or a pipe cracked, the system lost efficiency immediately. Worse, repairs were difficult and expensive. Therefore, every section required careful planning. Materials mattered enormously. Stone channels worked perfectly for open aqueducts, but pressurized systems demanded something different. The Romans frequently used lead pipes. Modern readers tend to react strongly whenever lead appears in a historical story, usually for understandable reasons. Yet from an engineering perspective, lead offered significant advantages. It could be shaped relatively easily. It resisted corrosion reasonably well. Most importantly, it could withstand substantial pressure when properly manufactured. Roman craftsmen produced pipe sections that fitted together with surprising precision. Joints were sealed carefully because even minor leaks reduced performance. Somewhere in the empire, engineers undoubtedly spent frustrating afternoons staring at dripping connections while questioning the competence of whoever installed them. Human nature has remained remarkably consistent across the centuries. Once constructed, inverted siphons allowed water to cross terrain that would otherwise require monumental bridges. They represented a practical alternative whenever geography became inconvenient, and geography frequently became inconvenient. Roman cities existed across diverse landscapes. Hills, valleys, plateaus, and mountains rarely considered infrastructure requirements before existing. Engineers adapted accordingly. Some aqueduct systems combined multiple solutions within a single route. Channels disappeared underground, emerged onto bridges, entered pressure pipes, crossed valleys, and returned to open conduits. The water itself remained blissfully unaware of these complexities. It simply followed the path provided. While siphons solved one problem, they introduced another: pressure management. The deeper the valley, the greater the force acting on the pipes. Excessive pressure could damage infrastructure, reduce lifespan, and create maintenance nightmares. Roman engineers therefore balanced practicality against risk. Not every valley justified a siphon. Not every bridge justified construction. Decisions depended upon local conditions, available resources, and engineering judgment. Sometimes the most impressive achievement was knowing which solution not to use. That level of restraint rarely receives the appreciation it deserves. Back in the cities, citizens enjoyed the results without necessarily understanding the mechanisms. Water arrived consistently. Fountains flowed. Baths operated. Public life continued. Few people spent their afternoons contemplating pressure gradients or hydraulic systems. Most were occupied with ordinary concerns. Yet hidden beneath everyday convenience existed an intricate network of engineering decisions. Every successful fountain represented thousands of choices made correctly. Every flowing bathhouse reflected countless calculations performed by individuals whose names history largely forgot. The scale of Roman bath complexes alone demonstrates how successful these systems became. Public baths consumed astonishing amounts of water. Pools required filling. Steam rooms needed supply. Cleaning operations demanded constant flow. Entire social institutions depended upon infrastructure functioning reliably. Visitors entering a large bathhouse encountered what felt like abundance. Water appeared everywhere. Hot baths, cold baths, fountains, pools, and washing facilities operated simultaneously. Such luxury required extraordinary logistical support. Without aqueducts and sophisticated distribution networks, these centers of Roman life could not exist. Wealthier citizens occasionally secured private water connections. Having water delivered directly to one's home represented status as much as convenience. It signaled wealth, influence, and access. Yet even private supplies ultimately depended upon public infrastructure. The system functioned because it served entire communities. Individual privilege rested atop collective engineering. This arrangement occasionally produced disputes. Illegal connections appeared. Unauthorized diversions occurred. Water theft existed because wherever something valuable flows, someone eventually attempts to redirect it. Roman authorities responded with regulations, inspections, and penalties. Infrastructure required protection. Otherwise, clever engineering risked becoming creative chaos. As aqueduct networks expanded across the empire, local populations developed increasing confidence in their reliability. This confidence was largely justified. Many systems operated for centuries. Maintenance crews inspected channels, removed sediment, repaired damage, and monitored performance. Roman infrastructure succeeded not only because it was built well, but because it was maintained consistently. Neglect destroys engineering faster than time. The Romans understood this reality. They invested in upkeep because replacement costs proved even less appealing. Travelers moving between cities encountered aqueducts regularly. Some crossed valleys on towering arches visible for miles. Others vanished underground entirely. Together, they formed one of the ancient world's most extensive infrastructure networks. Water linked distant landscapes to urban centers. Springs hidden in mountains supplied communities far away. Nature and engineering cooperated through careful design. And everywhere gravity remained the silent partner, making everything possible. By now, the Romans had accomplished something extraordinary. They moved water across vast distances through difficult terrain and into thriving cities without pumps or engines. Yet the journey was not complete. Bringing water to a city solved only half the challenge. Once it arrived, it needed organization, control, distribution. Because abundant water without management creates confusion remarkably quickly. Fortunately, Roman engineers loved organization almost as much as they loved construction. The next stage of the story would reveal how they transformed flowing water into a carefully regulated urban resource capable of supporting one of history's greatest civilizations. And like every previous chapter, the secret would not involve breaking the rules of nature. It would involve understanding them better than anyone else. By the time the water completed its long journey from distant springs and mountain sources, it had already crossed valleys, slipped through tunnels, followed invisible slopes, survived pressure systems, and traveled farther than most Roman citizens ever would. But arriving at the city was not the end of the process. In many ways, it was only the beginning. Because bringing water to thousands of people creates a new challenge, almost immediately. Who gets it first? How much does each place receive? What happens when demand exceeds supply? And perhaps most importantly, how do you stop everyone from taking more than their fair share? These questions sound surprisingly modern because they are. Human beings have always been very good at wanting resources and considerably less enthusiastic about sharing them. The Romans understood this reality better than most. So before the water entered homes, baths, fountains, workshops, and public buildings, It usually arrived at one of the most important yet least celebrated structures in the entire system, the castellum. To an ordinary citizen, the castellum might have looked unimpressive. It lacked the towering grandeur of an aqueduct bridge and possessed none of the visual drama of a public fountain. Yet without it, much of the system would have collapsed into chaos. The castellum served as a distribution center, a control point where water could be managed, redirected, slowed, and allocated according to the city's needs. Imagine a busy crossroads where every road in the empire suddenly meets. That was essentially what the castellum represented for water. Streams entering from the aqueduct were collected into a central reservoir. Here, the flow calmed, sediment settled, pressure equalized. Engineers could assess conditions and direct water into different channels leading throughout the city.